This is a video tutorial for tutorial 5A, question 6. Question 6 wants us to do some differentiation of functions involving, or expressions involving, the exponential function. The first one it wants us to differentiate is this, e to the x over e to the x plus e to the minus x. How do we do this? Well, the first thing we want to do is we recognize that this is a quotient rule problem. So, what is the quotient rule? If you recall, the quotient rule says if I am differentiating with respect to x the function u divided by the function v, that's going to be differentiate u, keep v constant, minus keep u constant, differentiate v, the whole thing over v squared. So, what do we get? Well, this is differentiate the whole thing over v squared. Okay. So the whole thing's going to be over e to the x plus e to the minus x squared. Right. Now differentiate the top line, you get e to the x. Hold v constant, you get e to the x plus e to the minus x. Minus, hold the top line constant, e to the x. Differentiate the bottom line, you'd get e to the x minus e to the minus x. So this is the derivative. Now we just need to simplify it slightly. So what is this going to be? E to the x is clearly a common factor, and we get e to the x plus e to the minus x minus e to the x plus e to the minus x over e to the x plus e to the minus x squared. And that's going to be e to the x times, you can see this and this cancel out, then I'm left with 2e to the minus x over e to the x plus e to the minus x squared. You can see this and this cancel out, this leaves us with 2 over e to the x plus e to the minus x. Now you may notice, however, that that's not the final answer given in your answer key, right? So what should I do? Well, I can actually, sorry, I forgot a squared here. I could leave it like this, there's nothing wrong with it, but I can also expand out the bottom line. So just for fun, let's expand out the bottom line. I get e to the 2x plus 2 plus e to the minus 2x, expanding this out. Right, so what can I do here? Well, I can multiply through by e to the minus 2x so that there's nothing with a negative coefficient, negative power. So this is e to the minus 2x, e to the 4x plus 2e to the 2x plus 1. Now, e to the negative 2x on the bottom line is the same as e to the 2x on the top line. And if you look at this expression on the bottom line, this is just e to the 2x plus 1 whole thing squared. So this is an alternate form, and you can also get that if you simplify first at the start. So it doesn't matter if you end up with this version or if you end up with this version, both are perfectly acceptable. So that brings us to the end of part A. Let's take a look at part B. So 6b wants us to differentiate e to the sine of x, sine squared x, sorry, times e to the minus x squared plus 1. Okay, so how are we going to do this? Well, this is a product rule question. We can just dive straight into this if we like. So we're going to hold the first one constant, e to the sine squared x, differentiate the second one. So differentiate 1, you get 0, differentiate this, you're going to get minus 2x e to the minus x squared. So the e to the minus x squared, differentiate e, you get back e, keep that constant, then differentiate negative x squared, you get negative 2x plus So now we keep the other one constant, e to the minus x squared plus 1. Sorry, plus 1. It's a bit messy. Times, so differentiate e, you still get e to the sine squared x. Differentiate sine squared, the 2 comes down the front, keep the inside constant, decrease the power by 1, so we get sine x to the power of 1. Differentiate sine x, you get cosine x. So this is what you get. Right, so what can we do with it? This is e to the sine squared x minus 2x e to the minus x squared plus e to the minus x squared plus 1 e to the sine squared x plus times sine 2x. Combining 2 sine x cosine x. Now you'll notice that we're actually going to have a common factor running through some of this, which is going to be, which is actually e to the sine squared x. So I'm going to factorize that out now. So e to the sine squared x. What have I got left over? I've got minus 2x e to the minus x squared plus e to the minus x squared plus 1 sine 2x. And not a lot we can do here really. I'm actually okay if you ended here. However, you may also want to instead factorize out this e to the minus x squared. So you could also write this as e to the sine squared x, e to the minus x squared minus 2x plus sine 2x plus sine 2x. And that's also a perfectly valid form. So either of these two, wherever you ended, I think it should be okay. So that brings us then to B, to the end of B. Let's take a look at 6C. 6C asks us to differentiate. This one's a little trickier. It asks us to differentiate 2 to the power of tangent x. So I don't know how to differentiate 2 to the power of something. I know there is some rule, so it can be done. However, I do know how to differentiate e. So I'm just going to rewrite this as d dx. And if I want to differentiate e to the something, well, I haven't got an e to start with. What gets rid of e? Ln gets rid of e. So if I'm differentiating e to the ln of something, I haven't really changed it. So e and ln would cancel. This whole thing is still just 2 to the power of tangent x. But it's kind of useful if I write it like this, because I can change the form to be e to the tangent x times ln 2. Now this is just e to some power. I know how to differentiate this. So differentiating this, the e to the ln 2 tangent x remains the same. Then differentiate by the derivative, multiplied by the derivative of the top line. So differentiate ln 2 tangent x, I'm going to get ln 2 secant squared x. Now, what can I do? I can pretty much just change this back to the way it was. So this is 2 to the power of tangent x times ln 2 secant squared x. Now, a few of you may not like this idea of e to the ln, so there's another way using implicit differentiation. You say let y equal to 2 to the power of tangent x. And we use a similar trick. We know we got to get the x onto the bottom line or onto the same line as the y, so we take ln of both sides. Ln y is equal to ln 2 to the power of tangent x. Using the laws of logarithms, we can bring that tangent x down. So ln y is equal to tangent x ln times ln 2. Now I can differentiate both sides with respect to x. What do I get? Differentiate ln y, I'm going to get 1 over y times the derivative of the inside, which is going to be dy by dx, is equal to, ln 2 is just a constant, tangent x I get secant squared x. So that means dy by dx is equal to y ln 2 secant squared x, but I know what y is. So dy by dx is equal to 2 to the power of tangent x ln 2 secant squared x. Again, two ways to get to the same answer. That brings us to the end of 6c. Right, last one now. Let's take a look at 6d. 6d asks us to differentiate x to the power of ln x. So we need to use a similar trick to last time. So you can always say let y equal to x ln x here and use the same trick that we did last time. I personally prefer to use the e straight away. So this is e to the ln x to the ln x. Then I can use my laws of logarithms to bring that down. So this is differentiate e to the power of the x. So the ln x comes down the front. This is ln x ln x. So this is differentiate e to the ln x whole thing squared. Now notice even the ln is in brackets here, so I can't bring that power 2 down this time. But I can differentiate this. What do I get? Differentiate e, nothing happens. This is still going to be e to the ln x whole thing squared. Differentiate the power. 2 comes down. Keep ln x constant. Decrease the power by 1. Differentiate ln x, you get 1 over x. So if we simplify, well, we can see from up here that e to the ln x whole thing squared is just x to the power of ln x times 2 over x ln x. So that is our final answer. How would you do it if you tried this method? Again, we start by taking ln on both sides. Use the laws of logarithms to bring the ln x down. So this is ln x. Differentiate both sides. And we get 1 over y dy by dx, differentiating the inside with the chain rule. This is of course ln of x, whole thing squared. So the 2 comes down the front, keep the inside constant, differentiate the inside. That means dy by dx is equal to 2 ln x times y over x. That means that dy by dx, substituting in for y, is equal to 2 ln x over x times x to the power of ln x. So again, two ways to get to the same answer here. Whichever you prefer is fine. That brings us to the end of question 6.